So, all right. We are looking at, of course, this is our Wednesday night session, so there'll be the Friday and Saturday as well this week, and then next week will be Monday, Tuesday, Wednesday. So, just to be aware of that, looking forward. But you should be hearing audio. I am talking. I never know how long I need to talk while this thing is going on. I guess that's why people just read the thing, even though it doesn't make sense to say it to people who can't hear you. But hopefully by now you've had time to look at this and see some things to try if you're not getting sound. And as always, you have different options to participate. You can use the chat to ask questions, you can raise your hand, you can use reactions, which is how you raise your hand, but you can then turn on your microphone and speak. I have a planned set of things to look at, but also then also if you have specific things that you want to ask about or look at, we can also do that. So today we'll be looking at properties of logarithms, solving logarithmic and exponential equations, and applications of exponential equations. We'll see how far we get. I'm going to focus more so, like I'm starting with module 7a content, which is the properties of logarithms and the equations, and then see how far I get into the more applications of those. But if I don't get to them, they will certainly be covered in the Friday and Saturday sessions. So this slide just shows where you go. You should have links to that live lecture schedule, various places, but that's where you access the recordings as well as the schedule. You just have to make sure you're signed into your Ivy Tech Google account. So, all right, we'll come back to this slide. Slide later with the feedback form, but for now we're going to here. So first thing I want to draw your attention to is the majority of what's on the formula sheet. So this is just a screenshot of part of the formula sheet, but that would be relevant to the final exam. But you see almost all of this then is logarithm properties. So we have all these log properties, but then also we have a few things from section 6.7 and 6.8. So pretty much all section 6.5, which also then gets applied to 6.7, 6.6, 6.7, and 6.8. But then you have these directly from 6.8 and 6.7, and honestly the PRT you're not going to use for this. That more applied back in section 1.7 when you were doing those like interest 1 year at a time. Pretty much when you're doing interest in 6.7, it's going to be these compound interest formulas. So those formulas, the properties of logarithms, those formulas, you don't have to have them memorized because they're on the formula sheet. You do have to know how to use them and when to use them. So that's what we'll talk about. And let's actually kind of like to make this bigger. I don't know. Now, okay. So one thing to note with these properties of logarithms, because that's what we're going to start with, is when you see these equals, all these equals you can think of as going both directions. So you can replace log base b of b to the x with any number, or you could take a number and turn it into log of some base. You know, I could take 5 and rewrite it as log base 3 of 3 to the 5th if I wanted to. It goes both ways. But then especially on these, you know, product rule and the quotient rule and the power rule, and even the change of base rule, recognizing you might start with the right side and need to turn it into the left side, or you might start with the left side and need to turn it into the right side. The other thing, of course, is don't try to make up your own rules. These rules, it's not like somebody said, I'm going to make up logs and I'm going to make up the rules that are going to determine how logs work. It's more like somebody said, I'm going to make up logs as the inverse of exponents. You have the laws of exponents that are determined by the definition of exponents. So you have let's see, so we have like, a power means that you're multiplying that thing together that many times. That's the definition. Based on that, everything else, all the laws of exponents are predetermined based on that and based on how multiplication works. So then, a to the m times a to the n is a to the m plus n. A to the m divided by a to the n is a to the m minus n. A to the m to the n power would be a to the m times n. A to the -1 is 1 over a to the negative n would be 1 over a to the n. A to the m over n is equivalent to nth root of a to the m. All of these things, so all those all of those exponent properties. Then the logarithm is defined as the inverse of the exponent. Based on that definition, all of these log properties are built. So again, they aren't made up as rules that somebody just wanted to have. They are the rules of how it works. It's like the law of gravity. Nobody was like, well, I think it would be nice if things, fell back to earth when you throw them up. It's just the way it is. So you can't just make up something that's not in these. The other thing, so it's not about the specific letters or variables that are used, is about the position of things. So you have the base of the log, you have the stuff inside the log, you have something being multiplied by the log, you have a power of the thing inside the log, all these, so it's all about the positions of things relative to each other. One thing that is not on here, to keep in mind, is just the relationship between logs and exponents, which is that if, and I'm just going to write it without even using any letters, is if I have a thing to a power equal to another thing, then I can convert that into exponent or into logarithm form. It's going to be log, the base of the log corresponds to the base of the power, and then it's of what the exponent was equal to, and then the log is equal to the power from the exponent form. So it's again about the positions. You could use any letters for any of those, but I just use shape so that it's to more kind of emphasize that it's about the positions. All right, so we're going to look at some examples of using these log properties. So starting, this is homework, module 7a homework. I'm going to start with question number 24. So in this question, you are, it says, write the expression as a sum and or difference of logarithms. So we're expanding this out so that we don't have any multiplication or division or powers left inside the logs. All of that has been expanded out into separate logs. So I'm using the quotient rule, and I'm using the power rule here. So, or sorry, not the quotient, we're using the product rule and the power rule. So I would start with the product rule. So I have things being multiplied inside the log. I can split that into two separate logs. So I'm going to have ln of x to the 9th. And then the power rule or the product rule says that's going to be plus ln of square root of 4 minus x. Now I'm going to rewrite this square root of 4 minus x as 4 minus x to the 1/2 power. So when you see a radical within a logarithm, you really want, it's going to be better to think of that radical in its exponent form. So square root is 1/2 power. Then the power, as long as the power is applied to everything inside the log, it can move out front. You just have to watch, if I had like log of 2x squared, since only this x is being squared, that would not be 2 times log 2x. So it has to be everything in the log. So we get 9 ln x plus 1/2 ln of 4 minus x. There's no rule that lets us do anything to further simplify or expand or do anything with addition or subtraction inside of a log. So this is as far as it's going to get. So I'm going to put in the 9. I need to type the letters ln then it'll turn bold, you know, you've done it right. And then the x, and then plus, again, so 1/2, and then ln parentheses 4 minus x, so that it knows that whole thing is going in to the log. So then I'm going to look at number 26, which is also an expanding, writing out as a sum and difference of logarithm, express powers as factors. But here we have kind of all three. We have the product rule and the quotient rule and the power rule. And again, I'm going to apply the product rule and the quotient rule first, and then the power rule. So this is going to be log and basically you can look at, you know, this stuff that's being multiplied, that's all going to get added. So I have the log x plus log x plus 7, but then the x plus 4 to the 4th that's on the bottom, that's going to be subtracted. So minus log x plus 4 to the 4th. So we're taking the multiple factors inside the log and turning them into addition and subtraction of multiple logs. And then we have the one power that's going to move out front and become multiplication. So putting this in, this is just a log, so log base 10, since there's no log written, but I just need to type the log x plus log x plus 7, and then minus 4 log x plus 4. And trying not to capitalize things that should be capitalized, but getting that in there. So next I'm going to look at number 32. So here we're using, this is about evaluating the logarithm. So potentially using the change of base property. Now, depending on your calculator, you may or may not really have to use the change of base property. So some calculators have a button that looks something like this, or something where you have a base and you can put in any base log. So if you have a calculator that can do that, you can just put the log base whatever of whatever, you know, any of those into your calculator. If you don't have that, if all you have is the log and the ln, then you have to use the change of base formula. And the reason some calculators only have the log and the ln is because the change of base formula exists, so you don't have to have any base log. So what the change of base property says is, I have that log, I want to have a different base, so typically either a common log or the natural log. And so it becomes then a division of those two logarithms. So we're going to have log 5 over log 1/2. So notice the base goes to the bottom, the input or the argument goes to the top. But we now have a different base log. It's not base 1/2 anymore. If I don't write a base, it's base 10, or I could do it as ln of 5 over ln of 1/2, and can put that into my calculator. So if I'm like on the computer calculator here, you know, then I can do, and here I have to do, I think I put in the argument first. So 5, put in 5 ln divided by 0.5 ln, and then equals, and get that result. Or I can do the same thing with log, so 5 and then log, and in most of your like handheld calculators, you would hit the log button first and then put in the number. But the computer calculator does it slightly more like a non-scientific calculator. So doing it with the log, I get the exact same result, but if I mix the log and the ln, it's not going to work. It's got to be the same base on the top and the bottom. So something else though, with, of course, with this, then you have to follow. So this just says with the change base formula, so you're actually rewriting it. And it doesn't specify what base to use. So like log 5 over log 1/2. Yeah. and then evaluate. But so you want to watch the rounding instructions. So this says round to 4 decimal places. Make sure you're following correct rounding rules. But I did want to look at one other thing with the change of base formula. So this is question number 15. So here's an example of where you have to have the change of base formula. To evaluate without a calculator, you wouldn't be able to do that log base 3 of 2. 2 isn't a power of 3. 27 isn't a power of 2. But when we use the change of base formula, and I change the base on each of these, so then I would have log 2 over log 3 times log 27 over log 2, then we get these log 2's cancel out. This becomes log 27 over log 3, and then I can either apply the change of base formula again, or I can pick and say, well, okay, with the change of base formula, I want the base to be base 3. Then log base 3 of 3 is 1. Log base 3 of 27 is 3, since 3 to the 3rd power is 27. And that's what log base 3 of 27 is asking. What power of 3 is 27? So you get that result. If you calculated log base 3 of 2 in the calculator, you would get some, big, long, complicated decimal, and log base 2 of 27. Likewise, you wouldn't think, looking at them, that they would come out exactly to a whole number, but they do. So that's, we'll see more of the properties of logarithms as we do the equation. So I'm going to move on then to solving the equations. So let's see. So with logarithm equations, that's what we're going to start with. You can get 2 possibilities. You can get something that you can end up having a log base, the base of something or other equal to a number. And if you get that form, then you can rewrite it as, the base to the power of that number equals whatever was inside the log. The other option is you can end up with log base something equal to the same base log of something else, and then the logs, you can kind of think of applying a base on both sides, canceling out, undoing the logs, and so you get just what was inside the log. The thing to watch out for, though, is you might have to do some work to get to this point. So if you have, multiple logarithms, they have to be combined in some way. If you have a log and then, stuff that's outside of the log, you can't undo the log until you have that log isolated. So that's where the properties come in. So I'm going to look at number 41. So here we have what's looking like we have a log equal to another log, so that direction, but I can't just immediately undo the log because I have stuff outside of the logarithms. So I need it to look exactly like log of stuff equal to log of other stuff. Right? So nothing outside the logs. So I apply the power rule, and now I'm starting with the number out front. I'm starting with the left side of the power rule, or I'm starting with the right side of the power rule and turning it into the left side. So I'm moving those powers, turning them in, or moving those factors, turning them into powers. And let me just zoom in here a little bit. So turning those factors into powers. So I get log base 3 of x to the 1/2 equals log base 3 of 2 squared. Then I can undo the log base 3 on both sides because that's all that's on that side is just log base 3 of something equals log base 3 of something else. And so we have x to the 1/2 equals 4. X to the 1/2 would be square root of x, or I can undo it. 1/2 times 2 is 1. So undo by squaring either way. So x equals 16. The other thing to watch for when you have these log equations is you always have to check for extraneous solutions, because the log input has to be positive, especially when you've combined multiple logarithms, when you've solved maybe a quadratic, but it's better to just, I think, be in the habit of checking always. So I'm going to just double check 16 could go into either of those original logs. So yeah, all is x is just going straight into the logarithm. 16 is positive, so it works. Now this is a setup and solve type. So first it wants you to rewrite without logarithms. So it wants you to get to that point of the process after we've undone the logarithms before we've finished solving. So the x to the 1/2 here, x to the 1/2 equals, let's see if it'll accept if I've already done that. Yeah, so it would also, I think, accept the 2 squared. But yeah, so just getting to that point of the process where you've undone the logs, but you haven't finished. Then you actually finish and solve it. So you just have to watch on those. Sometimes figuring out exactly which step they want might be a little rough. But yeah, number 44 then. Right, so here we have multiple logs on the one side equal to a number. So we're looking more like this second form where we have a log equal to a number, but we need to combine those 2 logs into a single log. I can't undo the log and rewrite an exponent form if I have multiple logs going on. So I'm going to apply the power rule and the product rule because I have addition. So moving the 2 to the inside. So log base 4 of x minus 3 squared plus log base 4 of 16, but then the x minus 3 squared and the 16 get multiplied together. So that becomes log base 4 of 16 times x minus 3 squared equals 3. Then I can apply, and I actually think of it as using this property. So I'm going to undo the log base b by applying a base 4 to both sides, because that's on the formula sheet. This relationship isn't on the formula sheet as far as going directly to the exponent form. But if you have, the base is the undoer for the log, then you can get there. So 4 cubed, 16 times x minus 3 squared equals 4 cubed. And 4 cubed is 4 squared times another 4, and that's the 16. So I'm going to kind of get rid of that 16 so I don't have to mess with it. So I have x minus 3 squared equals 4. You could even have simplified. Another way to do this is to evaluate log base 4 of 16. So that's just 2, and then you would have log base 4 of x minus 3 squared plus 2 equals 3. You move the 2 over, and you get, then log base 4 of x minus 3 squared equals 1. Then you get x to the x minus 3 squared equals 4. Either way. So this becomes then x squared minus 6x plus 9 equals 4. Move the 4 over. X squared minus 6x plus 5 equals 0. And that's x minus 5 times x minus 1. Works to factor that. So we would have 1 and 5 as the potential solutions. But if I look back at that original equation, if I plug 1 into that, I would be trying to take a log of 1 minus 3, which is -2. I can't take the log of a negative number. So 1 would be an extraneous solution. 5, though, works. 5 minus 3 is positive. But again, they wanted this rewritten without logarithms. So they want that step at the point where the logs have been undone. Let's see if it'll accept 16 times x minus 3 squared equal to 4 cubed. Yeah, so it's not real picky about It just wants some point in the process after the logs have been removed, and then without doing a lot of testing, it seems like it might be somewhat flexible as far as how much simplification you have or haven't done on that. Because I'm sure it would also equally accept x minus 3 squared equals 4. But I can't really reverse and go back to test that. But yeah, so then the solution set, of course, if you put in 1 and 5, it will just completely be like, nope, that's wrong. Let's see if it'll say anything about it. I mean, it does give some hints, so remove any extraneous solutions, which hasn't been done, but it doesn't just say that, so you don't know what part of this whole process you might have done wrong. But in this case, remove the 1 because it doesn't actually work, then it's good. All right, so then next I want to look at number 46. So here we have a log on one side, the other side we have a number and a log. So there's several different ways I can approach this. One is to get it into that first form. So getting it logs on one side, number on the other. So I move this log over. So I now have log of 8x plus 7 minus log of x minus 1 equal to 1. These logs then combine, so it's going to be log of, and because it's subtraction, 8x plus 7 over x minus 1 equal to 1. So applying the quotient rule, starting with the right side, turning it into the left side. And then this is a base 10 log, and the base is not written, it's base 10. So I apply that base to both sides and get 8x plus 7 over x minus 1 equals 10 to the 1 power, but that's just 10. Another way to approach this is to actually use this inverse property in reverse and rewrite 1 as log, in this case would be log of 10 to the 1. So then I would end up with log 8x plus 7 equals log 10 plus log x minus 1. Combine using the product rule. This would be log of 10 times x minus 1 equal to log 8x plus 7. Then the logs can cancel once it's just a log equal to a log. And I get 8x plus 7 equals 10 times x minus 1, which I also could get, that would be the next step here. So as long as you're correctly applying logarithm properties, there's different routes you can take to get to the same point. But at this point then, solving this, this is 10x minus 10, and I subtract 8x from both sides. So 7 equals 2x minus 10, add the 10, 2x equals 17, then x equals 17 halves. And double check, let's see, 17 halves is bigger than 1, so that's fine. And then the 8x plus 7, as long as I have something positive, it's certainly going to work. So nothing to cause that solution to be extraneous. I always just double check when I'm doing these just in case I mess something up along the way. But that would be the process. A couple possible processes when you have that mix of logs and numbers. All right, one more example of this, number 49. So here I have multiple logs, and this is one where it's really tempting to just cross off all of the logs. So that's not following the correct process. So this is not going to just be 2 times x minus 2 minus 125 equals 5. That would be fully incorrect. So I have to first combine, so it's a single log. Now it's already a single log on the right side, but I need to combine to a single log on the left side. So move that 2 inside. So it's squared, and then these are subtractions. So it's going to end up being log base 13 of x minus 2 squared over 125 equals log base 13 of 5. Now the logs can cancel out. But notice the 2 had to become a power, not being multiplied by the x minus 2. The 125 is divided, not subtracted. So having that correct combination of those numbers and expressions with the log. And then you can solve. And so this would be like x minus 2 squared equals, let's see, 5 times 125 is, I believe, 625, but I can do square root then, plus or minus square root of 625, which is plus or minus 25. So x minus 2 equals positive 25 or negative 25. Add 2 to both, and I get 27 or negative 23. But again, when I go back and check for extraneous solutions, 27 minus 2 is fine. Negative 23 minus 2 is not okay. That would be a negative input into the log. That doesn't work. So only 27 is actually the solution to that. All right. Interesting. They also ask you then, so if you had like a square root or something in there, they're asking you to then go ahead and approximate it. In this case, there weren't any such thing. We just had the number 27, so it didn't need to do that. All right, so then the last thing in this section is exponential equations. So the main thing with exponential equations is you want to isolate the exponent. So anything that's, being added to the exponential expression or multiplied or anything, you want to get it to where it's just something to a power equals something. So you want something like this. Then you can apply the log. With whatever base the exponent is to both sides of that. So there's not actually a lot of these. You'll see a lot more of these in 7b. But looking at number 50. So one thing is, if you can actually get b to a power equals b to another power, then the b's, you apply the log to both sides and it cancels out both bases. So if you look here, I have 7 to the x minus 7 equals 49, but I recognize 49 is also a power of 7. So 7 to the x minus 7 equals 7 squared. Then the bases go away. X minus 7 equals 2. And I go from there. So sometimes it gets a little bit more complicated than that. I think we'll see in, let's see, oh, yeah. If I had something like 16 to the x equals 8 to the 3x or something, then I'd have to recognize 16 is 2 to the 4th, 8 is 2 cubed, and I have that matching base then. So we would have the 4x and the 3 times the 3x, etc. So you might have to manipulate one or both sides to get them to be a power of the same base, but it's still going to be easier to do that than necessarily than to start working with the logs. You'll have to do it eventually to evaluate the logs. If you do use the logs, you'll still eventually have to recognize the 8 and the 16 as as what they are, as powers of 2. So then number 51 is using U substitution, as is number 52. So you have to recognize the squares. So here you have 2 to the 2x. So if you recognize that as actually 2x squared, or 2 to the x squared plus 2 to the x minus 42, then you can say u equals 2 to the x, and we have u squared plus u minus 42. You solve that for u, whatever u equals, then you replace the u back with 2 to the x, and you can solve those two equations. But I'm going to spend a little bit more time on this next one instead. So number 52. So here I have to recognize I have my 2 to the x, multiple of 2 to the x, and then I have to recognize 4 to the x is 2 to the x squared. So it's 2 squared to the x, which we had in the previous one, which is 2 to the x squared. So again, u equals 2 to the x, then I have u squared minus 22u, and then I need to add the 121 to both sides. So plus 121 equals 0. This becomes u minus 11 times another u minus 11. So I actually end up with just the one solution, u equals 11. Then that means 2 to the x equals 11, substituting back in for u. And so then I would apply log base 2 potentially to both sides. You could do other base logs depending, like if you can't calculate log base 2 of 11 on your calculator, then you might want to just default to applying a common log or a natural log. So we get x equals log base 2 of 11. And they want not a calculator result, they just want the actual exact answer log. So I would type in to get the base. I either can, you know, if you do the more button, you can get the, well, maybe somewhere. Oh, you do the subscript, or the other way to get to that subscript is if you type an underscore. So log base 2, and then make sure you're out of the subscript to get the 11. So, so that's that process. And then number 53 is evaluating. So you have a function that's an exponential model, exponential function, and we're putting in so the v, the value, or sorry, we're not plugging in. So that's the value, and then t is the time. So if it says when will the car be worth each of the following amounts, we're solving for time. So we're setting this 14,364 times 0.82 to the t equal to 8,000. You can't multiply the 14,364 times the 0.82. That violates order of operations. We have to first isolate the exponent by dividing by the 14,364. And then we get a 0.82 to the t. Now, the final answer here needs to be rounded to the nearest tenth. My recommendation is don't round anything until the final answer, but if you are going to round, if your final rounding is to the nearest tenth, then maybe round to the nearest hundredth or thousandths or a few decimal points past what the final answer should be. So if you introduce some imprecision, it's not enough to affect the final answer. But 0.82 to the t, I'm just going to say equals this fraction. Then I'm going to apply, what I'm going to do is I'm going to apply a natural log to both sides. Then that allows the t to move out front using the power rule. So t times ln of 0.82 equals ln of this stuff. And then I divide by the ln of 0.82, or this whole thing could be done as a log base 0.82 of the 8,000 divided by 14,364. So on this calculator, the way I can do it, and you can do this on your calculator as well, you could do the division. I'm not going to write down that answer. I'm just going to say the next step is take the log of that, or ln, if I want to do, so I guess I'm switching to log instead of ln. So log of that, and then divided by, and in this case, I have to type in 0.82 and then hit log, or you put log of 0.82. to get the result 2.94. That runs to 2.9 years. Let's see, it's starting. It's pretty quick, but right. So I'm not going to do all of those, but that would be the process you'd use for each of those. Again, the actual, like how you calculate it is going to somewhat depend on what calculator you have. All right, so that's what I had to look at from 7A. Again, just there's a lot of fairly quick questions that are just using the product rule and the quotient rule and the power rule, doing those solving. But I'm going to switch over to 7B. So 7B, we have section 6.7, which is financial models. So this is applying using exponential equations, but now we're putting particular meaning to the pieces. So we have these interest formulas. And let's see, I'm going to go ahead and just bunch of this stuff. So mainly you want to pay attention to these interest formulas. The first one you're going to use when it says compounded, pretty much when you see the word compounded with anything other than continuously. So it might be annually or quarterly, monthly. Those are the most common ones. So in this one, P is the principal. So that's the amount that's been invested or borrowed or put in some way. And then R is the annual interest rate, sometimes referred to as the APR, and it has to be in decimal form. If you struggle converting a percent to a decimal, the percent symbol, that means percent. Per cent, per means divide, cent means 100. Century, cents in a dollar, cent is 100. So you replace the percent symbol with divided by 100 to convert. But it's always going to move the decimal 2 places to the left when you do that. So if you're comfortable doing that, certainly that's fine. If not, do the division by 100 and you should be good. And then N that you see twice in this equation. So this is right a little bit bigger. A equals P times 1 plus R over N to the NT. So the N shows up 2 places there. That's the number of times compounded per year. So basically you have that annual interest rate, but if you're adding interest on once a month, then you're only getting a 12th of the interest each time it gets added on, but you're also getting it 12 times a year. So the rate gets converted to the monthly rate and the time gets converted to the number of months. And likewise, so N number of times compounded per year, 8 for annually, that would be 1. For quarterly, it would be 4 quarters in a dollar, 4 quarters in a year. Monthly would be 12. If it was daily, it would be 365, etc. So those are mainly what you have. And then T is going to be the number of years. Now, if you see compounded and it says continuously, then you're going to go to the continuous interest, and you even see that word continuous. So now the 1 plus R over N to the N part has been replaced with E to the R. The R is still the annual interest rate. T is still the number of years. P is still the principal. notice when you get the uninhibited growth or decay formula, this is really the exact same thing as PE to the RT. It's just different letters. The only difference is, I mean, the context, of course, but R in the compound interest, you're not going to have a negative interest rate. But when you have the uninhibited growth or decay, you could have a negative rate. So let's go ahead and look at some examples of this. So starting with number 4. And some of these I'm just going to set up. Some of them I'll kind of go through the process of putting in the calculator. But this is just a basic, this amount was invested. So just looking at recognizing the pieces of the equation. So this is compounded quarterly. So I'm going to use that first equation, A equals P times 1 plus R over N to the NT, with N equals 4. The $300 invested is P. The 10% means that R equals 0.10, moving that decimal to the correct form. After a period of 2 years, T is 2. So plugging it all in, you'd be calculating 300 times 1 plus 0.10 over 4 to the 4 times 2 power. Now, the thing to watch for when you're putting this in the calculator, a few things. So I can just put the whole thing in pretty much as is. Let's see. I lost my 300 times parentheses 1 plus 0.1 divided by 4 to the, and then if I do 4 times 2 right now, just as is, it's not going to work right. I have to put parentheses around that. We're going to put X, that's 4 times 2. Or I could just put in the 8. But if I did it, to the 4 times 2, whatever else is going on, it would do all this stuff and then do that result times 2 instead of having the times 2 be part of the power. Again, depending on your calculator, you may or may not have to worry about that. You don't want to take the 0.10 divided by 4 and round. Now, in this case, you wouldn't really have to round, but if it was 0.10 divided by 3 or something, and then you round it, you don't want to do any rounding along the way. So you just want to really do it all at once. And then, of course, make sure if you are doing it steps at a time, the first thing you might, start with 0.10 divided by 4, 0.1 divided by 4, add to the 1, then take that to the 8th power, then take that times the 300. But you wouldn't take the 300 times that base before taking the 8th power. So just make sure you're following correct order of operations. You should get a number, depending on the interest rate and the amount of time. 365 from 300, sounds reasonable. But if I came up with something that was like less than 300, or that was like thousands of dollars from 2 years of investing $300, if you know anything about how money works, you should be able to recognize if your answer totally doesn't make sense. And then you round to the nearest cent. So yeah, that's, well, I might as well go home. 365.52. Yeah. So then I'm looking at number 5, which is similar, but now it says find the principal needed to get the given amount. So to get $700, so that's going to be A is 700. After 4 years, T is 4 at 10%, R is 0.1, compounded quarterly, N is 4. So now I'm plugging in 700 equals P times 1 plus 0.1 over 4 to the 4 times 4. So all I have to do is I'm going to take, instead of taking something times this whole thing, I'm going to take the 700 divided by that whole thing. So I can still do it kind of all at once in the calculator. I'm just doing 700 divided by, and then the 1 plus 0.1 divided by 4 to the, and I'm just going to type into the 16th power. And I should then get something less because I'm putting that amount in. It's going to gain interest and get to the $700. So again, pay attention to what's being asked and what makes sense as an answer, and that'll help catch if you made little mistakes, with the calculation or anything. Then number 10. Here it says what rate of interest. So that means R is the unknown, compounded annually, so n equals 1, required to triple an investment. So that doesn't tell us, we don't have a principal or an end result, but we do know that A is going to be 3 times P. We want the end result to be triple the principal invested. And then we have T is 18. So plugging this in, we have 3P equals P times 1 plus R, unknown R, over 1 to the 1 times 18 power. Simplifying that a little bit. Now, the other thing you could do with this tripling is pick any random number you want for P. And the easiest thing to do is pick 1. But either way, I can divide both sides by P and it goes away, or I can plug something in for P and it'll go away. Some way, but so I get 3 equals 1 plus R to the 18th power. To get to R, I need to undo the 18th power. So I'm going to take this to the 1/18th power on both sides. So 1 plus R equals 3 to the 1/18th power. So I can do that calculation. Three to the, you could also do this as the 18th root of 3, depending again what buttons you have available. So I got 1.0629. So when you see that value, so 1.0629, whatever, the 1 is the one part that got added on, and then starting here, like this would be, the percent. So if I subtract off the 1, I have the 0.0629, that's a 6.29, and 2 decimals place, 6.29%. But you might get to the point, if you, at least if you're using these a lot, to where you don't even have to do the subtracting one and dividing. You can look at that 1.0629 and recognize, okay, that's a 6.29% interest rate happening there. Next up, I want to look at number 11, just part A. How long does it take? So now we're looking for the time. How long does it take? In fact, I think I'll actually do the second one because we haven't done a continuously compounded yet. So compounded continuously, you would use A equals PE to the RT. We're solving for T. The 14% means R is 0.14. Actually, do the setup for both, I guess. Quarterly, we would have, so this is to double in value. So I'm going to do that. I'm going to pick, say, P equals 1, then A equals 2. So 2 equals 1 times 1 plus 0.14 for R over 4 for compounded quarterly to the 4 times the unknown T, or with the P, it was a continuously 2 equals 1 times E to the 0.14 T. So yeah, the solving process is a little bit different. So here, for the first one, I would need to, rather than trying to mess with finding this base or mess with this base, I'm just going to do a natural log on both sides. That allows the 4t using the power rule to move out front. So I have t times 4 times ln of 1 plus 0.14 over 4 equal to ln 2. Then t equals ln of 2 over 4 ln 1 plus 0.14 over 4. Kind of messy, but you can put that into your calculator carefully and come up with the result. And then this one, the continuous, is actually a little bit easier. 2 equals e to the 0.14t. When I do the ln on both sides, it actually cancels out the e. So ln of 2 equals 0.14t, divide by the 0.14. And we get t equals ln of 2 over 0.14. Again, put that into your calculator. Not nearly as many chances to mess up with that. But yeah, so you get those. I'll go ahead and do that. So let's see, for this first one, it's going to be 2 ln divided by, and then I'm going to have, I'm going to put parentheses 4 times, and then I have to put in, so I'm going to do parentheses again, 1 plus 0.14 divided by 4. Then I do the ln. Again, if you were on a standard calculator, you would press the ln button first. Close my parentheses, and I get 2 decimal places, 5.04 years. So let's see if, yeah, so that worked. And then for the continuous, it's just ln of 2 divided by the 0.14. So that goes a lot quicker, but it comes out, takes a little less time. The more often it's compounded, the faster it grows, although it's kind of a diminishing increase. But yeah, so that's finding the time with how long it takes to double. You might also be asked, I'm not going to go through this, but to find the time, how long will it take to get from a particular amount to another amount that might not be double of the first amount. And then I also want to look at number 19, just a little bit to talk about, because this looks big and messy. So we have here a lot of words. I'm going to focus on the formula. We have CPI equals CPI sub 0 times 1 plus R over 100 to the n. But it tells us, the CPI after n years. So n is the number of years. CPI is, that's the result. CPI sub 0 is the CPI at the beginning. So when it says the CPI was 152.2 for 1995 and 184.7 for 1999, then to plug into the formula, I would need, and it's saying what is the inflation rate. So solving for R here. But what I would plug in is we would have the 1995 would be the first year, the beginning of the period. So the 152.2 would be the CPI sub 0. The 184.7 would be the CPI. And then we have to figure out, well, from 1995 to 1999, 4 years. So n equals 4. So that's what you would plug in order to solve for R. And then notice they have the R over 100. So the conversion to percent, when you solve for R, it'll be the actual percentage, not the decimal form. But yeah, so that's the process you would use, and then you would have the CPI sub 0 and the R to plug in the N to plug in the 266 to solve for N. So somewhat complicated, but you just have to pay attention to what's being said and what the different variables and parameters represent. So that's pretty much our time. I didn't really look at 6.8 at all, other than the n sub 0 e to the kt. It would really be the same thing as p e to the rt. I do want to real quick look at, let's see, I'll do number 24. So if I want to come up with, and you'll have some of these questions where the first thing they want you to do is just put in the n sub 0 e to the kt. You're not finding anything, but then you have to actually come up with the formula to use. And so you have to figure out what k is, but you don't really have to figure out what k is. You really just have to figure out what e to the k is. So let me go ahead and, so this is n sub 0 e to the kt. So then they give this information. The population doubled in size over 18 months, and the current population is 70,000. So I use that information first to come up with the formula. So whatever n sub 0 was, I don't know. I do know that whatever that was, that when I plug in 18 months, t is time in years, so 1.5 years, that's going to give me double of the initial amount. I guess we're saying the 70,000 actually is the current, is the n sub 0. So 70,000. Or you could have that be, anyway, it doesn't really matter. 2 equals e to the k to the 1.5 power. I can apply a power of 1 over 1.5 on both sides. And that will give me e to the k equals 2 to the 1 over 1.5. And then what I can do is I have my n sub 0 being 70,000. And I want to think of the e to the kt as e to the k to the t power. So 70,000, then it's going to be 2 to the 1 over 1.5 to the t power, or 2 to the t over 1.5. With 70,000. In general, if you have the doubling time, then you would have, the initial value times 2 to the t over doubling time. If you have the half-life, you'll see on other problems, then you would end up with 1/2 to the t over whatever the half-life is. But you don't have to solve again all the way for k. You can just solve for e to the k. But yeah, there's Newton's law of cooling. I will tell you, you have it on the homework. I don't think you have it anywhere other than homework. So it's certainly not something you have to have memorized, even though it's not on the formula sheet. I'll just tell you that. But yeah, so solving for some of these where you're solving, it's going to be easier. If you do solve all the way for k, don't do any rounding. Keep it fully in exact value form. It's going to be less messy if you just solve for e to the k. But yeah, so you'll get more examples and stuff from 7B homework, especially if you come to the Friday and Saturday sessions, and then make sure Monday, Tuesday, Wednesday for next week. But let me just get you then the feedback form here. So just to let us know that you're here and how it was and all of that. So yeah, the Monday session I think is like 2 o'clock, and the Tuesday session 10 a.m. next week. That didn't work. Yeah, Monday 2 p.m. to 3 p.m. Tuesday 10 to 11 a.m. But Wednesday is still 6 to 7 next week for exam final exam review. So all right. Any questions before I close the room? All right, well, I'm gonna go ahead and close it. And thanks for being here.